Welcome back, dear students. We are going to our lesson 4 in our electrochemical reactions, and here it's going to be a short and sweet one. We're going to talk about the chloro-alkali industry. So here we'll actually be producing chlorine as one of the things that we will have. So we're going to produce the chlorine gas eventually, and we should have and you see it says chloro-alkali, means there is chlorine and then there is an alkali that we are actually producing, and the alkali that we are talking about here is sodium hydroxide. You know that it's an alkaline something, it's a base, this one, okay? So we're going to form these two. These will be our products actually, and well, you will notice that we have another product that we form. We just, let's call it a byproduct. That would be hydrogen. So you will also form hydrogen over there. So you have to just have an idea of why would we need to form chlorine and why sodium hydroxide. Well, chlorine is good for your detergents, and even you can use it in what is this one? When you're cleaning the swimming pools, I know that chlorine is used, and then even when you would like to treat water for drinking, you actually do. They use chlorine for that as well. So sodium hydroxide is mainly used for soap, so that one you must know its uses as well. Hydrogen, well, that can be used as fuel, isn't it? So it's a fuel for these, what do we call them again? Let's think first. Those NASA things, the rockets, yes. So it's fuel that can be used there, and it can be used in the medicine field as well. They sometimes need that. So that is the reason we're going to do the chloro-alkali industry. We are going to have this electrolytic cell again, so we can produce chlorine gas. As you are noticing here, there is chlorine gas going up here, and then hydrogen gas coming out as well. We will also form sodium hydroxide, but I think you're noticing we need a few raw materials as well. So which ones are our raw materials in this situation? Raw materials are things that we need to start off. So, well, in this situation, we actually just need what we call brine. Brine is just sodium chloride, really, people. So it is just sodium chloride, your usual salt itself. Okay, it just has to be concentrated when you start. So can you see that we have concentrated sodium hydroxide in this membrane cell? And then we also will need water. So let's just put water as one of the raw materials that we're going to need. As you can see, this one is pointing in water going in. Well, before I get started with this, I want you to know that the chloro-alkali industry, at first there were other cells that were formed before our acute membrane cell. So that was the diaphragm cell and the mercury cell. So these ones had some environmental problems, and they were not friendly to the environment, either to the workers, so they were phased out, most of them. So I would like you to notice that in mercury itself, it is poisonous to humans, even birds and animals, because it affects the nervous system, even the reproduction system. It can be affected by mercury, and the main problem is that it accumulates up in the food chain. Have you ever heard that they ate some mercury poisoned fish and then they were also poisoned? So what it means is, when we say that something accumulates in the food chain, it means if you eat the fish that was once poisoned by mercury, you will be poisoned as well. So that was just a very big threat for the mercury cell. That's why we don't talk about the mercury cell now. The diaphragm cell had asbestos in it. So because some parts of it was made of asbestos, well, because this asbestos here, if it was breathed into the lungs of these workers, it could cause problems, even such as cancer or respiratory problems may come out of this one. There is this disease called asbestosis. It comes from this as well. So that is why we use the membrane cell, we know that it has lower internal resistance, so the equipment used has lower internal resistance, so it means even on power we actually use less power to get this one going. So we mainly focus on the membrane cell, and when you're asked in your syllabus, it's mainly the membrane cell that they want. So let's go straight into how this thing works. So let me erase these raw materials. We may not need them for now. I think you will remember them. Just know if the uses of each one. Those are the easy things you may find anywhere. So go ahead and know 2 uses of each. You know, manufacturing of paint, those things, you know, you can include them in your uses. Right, what exactly happens? Well, here we have the setup of the membrane cell. As you can see, this one here is the anode, is positively charged. So we'll have a power supply as usual up here. So this definitely is the positive and this is the negative. So you can tell this is the power supply. So it's definitely an electrolytic cell. Okay? That one established. And by the way, it has to be direct current, otherwise some reactions will start reversing themselves here. We don't want that. All right, so now what happens? From what I told you, the moment you switch on this power supply, some form of electrolysis takes place. Can you see that in the raw materials, on the left-hand side, on the compartment, we have this part going in? Can you see it's concentrated sodium hydroxide that is going into solution? From what I said, that concentrated sodium hydroxide is going to ionize, and it is actually going to be in its ions. So there will be sodium plus and chlorine ion like that in aqueous form the moment the current starts flowing. So you can see that we have sodium here and chlorine in this compartment. Notice at this point we have something labeled membrane, and the membrane is porous, as you can see. In actual fact, let me just tell you this, it's a selectively permeable membrane. So what do we mean by selectively permeable? It means it will let some ions pass through and some ions they won't pass through. So it's a selectively permeable membrane. It's the reason some things will happen just now. Okay, what do I mean? Please, the only thing that will pass via this membrane are cations. They have, if you are positively charged, well, you can pass through the membrane. As you can see, sodium plus made it. Well, as you can see here, we had sodium chloride and we had a bit of chlorine like this. So chlorine is not going to go that side at all, because then it is negatively charged. It's an anion. This membrane will only let sodium through, only positively charged things. That is how sodium is going to make it to the other side, that is to the cathode. Well, because at this point the anode, which in this situation is made up of titanium, we know that it is positively charged. From what I have indicated before, unlike charges will attract. So the chlorine here, which is negatively charged, as you are noticing, it will be attracted to the anode where it will be oxidized. So if something is oxidized, it loses electrons. So the chlorine is going to lose that extra electron that it has, and it will be something of this sort. But like I've already indicated earlier, you need to have 2 of them, because chlorine will only look good with a 2 over there. So since there are 2 of them, you will also get 2 electrons. So this right here is what is happening at the anode. And this is already the gas that we are forming, this part. As you can see, is chlorine gas going out. So this chlorine gas is what we just formed here at the anode reaction. So the anode half reaction is sorted out. We already have the chloro part of the chloro-alkali industry. So we are making so much progress, right? Well, so I think you're noticing that these bubbles here are already here. These are the bubbles of chlorine going out, so they collect it over here, something to collect it. Well, since the sodium chloride was the one that was pumped into this side of the tank, you are noticing that the chlorine is going out and the sodium, like I said, it is going to go to the other side. So I think it's clear to you that the concentration of this sodium chloride that we started with, it will eventually decrease with time. So if the concentration is too low, we know that the reaction rates will actually decrease. So we don't want slow reactions. That is why after some time you actually have to take out the depleted sodium chloride. So the dilute sodium chloride is tapped out through this opening over there. So that one that goes out is dilute. The one that goes in, as you can see, it's concentrated. So keep that in mind. And why is it that it's dilute? It's because the sodium is going to that side and the chlorine is going out. So the ions are actually getting out of this. So the number of moles of ions is decreasing with time. Okay, now that sodium made it to the other side, well, remember the cathode itself, most of the times we know that the cathode is negatively charged, right? Because electrons that we lose, these electrons that we talked about, we say that they move from the anode right to the cathode. Well, the electrons are here, they are extra electrons over here, some negative charges. So sodium, as you are noticing, sodium will be looking forward to getting those electrons over there. So it also approaches the cathode. Well, sodium is looking forward to getting reduced to sodium atom, but it's not the only one there that is looking forward to getting the electrons. There is also this reactant that we talked about. This is water right here. It's also being pumped into the cathode compartment. So even water would like to get some of those electrons as well. So now it's a battle to get those electrons. So the stronger one will win here. The stronger guy will win. So since it's at the cathode, something that comes here has to be reduced. And if it is going to be reduced, it has to be the stronger oxidizing agent. So let's see quickly which one of the two is a stronger oxidizing agent between sodium and water. Let's see. The water reaction, I had it here in advance, but for you to see which one is stronger than which, we have to use our tables. So this is the reaction when water itself is getting reduced. So we just have to figure out what happens if I try to do this. You see, water is the one getting these 2 electrons. Sodium also would like to get 2 electrons and get sodium like this. So this whole thing can be settled by this on the other side. So we have to find the standard electrode potential and see which one is higher than the other. So let's see if we can do that using this one over here. Let me keep my red. The water one. Let's see if we get the correct one for water. It is not this one, is it? It is. Perfect. Then let's get the sodium one. So the water one, you can see that it's this part, right? So let's go and write this electrode potential if water is going to get 4 electrons like that. I'm worried about the oxygen involved there. So I think I have the incorrect, because here this has got oxygen, so it can't be this one. I want water getting electrons only. So let's keep looking, giving us hydrogen. That one right there. Perfect. Now that's the one that we want to use, that one. Now look at the electrode potential, it's negative 0.83. And besides, we want to compare which one is a stronger what? It's happening at the cathode, they're getting reduced, so we want a stronger oxidizing agent. So oxidizing power or oxidizing ability is increasing as we go down. So the one that is below the other one in 4B, it means it's the one that is a stronger oxidizing agent. So at this point, we are seeing the level of water. But before I go, I'm going to have to write that negative 0.83. Let me do that. Okay, And then let's go and look for sodium itself. Hopefully we find it. Okay. So we are expecting it to be somewhere. Let's see. That's a lot of questions from a November 2015 question paper. Well, that's not what we are looking for. We are looking for this one. I got the sodium right here. So can you see that it's negative 2.71? Besides, you can see that sodium is above our water reaction. Notice the water one is down here. So if you want to compare this one and the sodium one, you can see that the oxidizing ability increases as we go down. It means the water one is the one that is going to win in this situation. But if you want to use the numbers, let's write the negative 2.71. It's negative 2.71. If you still remember what I said if you have negative 2.71, it means you need 2.71 volts to force this reaction to take place. And here, you also have to force this one to take place, but you only need 0.83 volts. So if you were to choose, which one were you going to choose? Definitely, you were going to choose this reaction over here. So this particular one is going to be our anode half reaction. So keep that in mind. Now that we have our anode half reaction and our cathode half reaction, let me just do this quickly. In fact, since I had it in advance, let me move it properly there. So you know next time which one is your anode and your cathode half reaction. So let me remove all of this. Well, this one is not going to happen, and we know why it's not going to happen. This reaction won't happen, so the sodium will still be in solution. Well, if you still remember, the sodium is still there, but in this reaction, look at what we are forming now. We formed the hydrogen that we needed. Look, we are taking it out. Look at the right-hand side, this gas here. Can you see that it is the hydrogen gas? So that's the gas that we formed right here at the cathode. So remember, we said hydrogen was a byproduct. So here it is, and we know that it is this reaction over here that is responsible for that, for the formation of the hydrogen gas. It's not just forming hydrogen, it is forming this hydroxide ion. So sodium, this sodium, is not going to miss that chance again. So sodium, since it's still in solution, it is actually going to react now with the hydroxide that is formed in the top reaction, and that is how we are going to get the sodium hydroxide that we talked about. So this sodium hydroxide was one of the products that we wanted, and this is how we are going to get it. And as you can see, it's the one going out through here. Notice the sodium hydroxide is a product being tapped out of that. So we get it using this reaction over here. So to make sure you're not confused, the anode half reaction is this one where the chloride ion becomes chlorine, and the cathode half reaction is this one where water is reduced to form hydrogen and the hydroxide. You have to learn how to write a balanced or an overall reaction in this, because that's the important part as well. So how do you do that? I think we talked about this type of reactions. You can see that I have it here already in your notes. So I may have to try and hide it away from you for a while here so you can learn how to do it without looking. So how do you do it? Okay, so what you do is you're going to have to take your anode half reaction. So how do we find our net reaction or net ionic? Let's start with net ionic reaction. So all that you need is to take your anode reaction. So that was chlorine, like that, going to chlorine gas, giving you 2 electrons. Well, what was happening at the cathode? Well, water wasn't having a chance there, so there was water getting 2 electrons as well, and giving us hydrogen, and what else? The 2 hydroxide. You see, I just copied those two reactions that are there. In aqueous form, you may want to put state symbols. It just looks better. Okay, now that this is here, oh, these numbers are not visible. Okay, so it's water here and there, right? So now that we have that, let's see how to form the net ionic. So you just write what is on the left. So at this point, I'm noticing that it is 2 chloride, like that. I think it would be better if we put it in aqueous form. I'm noticing I didn't put the symbol even here. It's in aqueous form. All right, so that one plus the water, right? And then you're going to, and oh, before we finish that, do you see that I just went ahead and did this because this point here, do you see the electrons are balancing just fine? So that is why I didn't do any multiplication of these things. So I'm just taking them as they are. Well, on the right-hand side, there is that and that and that. So I just have to write that. So it's chlorine gas. We know that we form that. Hydrogen gas. And we also form some 2 of those OH minus. Well, so this is the net ionic reaction. So you may want to include your spectator ion. You know that when we started off, I never say that we'll have just a chloride ion floating around like that. It was actually in form of sodium chloride. So you may put your spectator ion back, this one, if you want, and then there will be sodium here as well to be added. So if you want to write it with its spectator ion, you may write it like this, but this won't be a net ionic now. It will be an overall, balanced overall reaction. So it will be 2 sodium chloride like this, plus 2 water. You're seeing that all I'm doing is to put sodium back. Okay, plus hydrogen here, and the 2 OH minus, we formed sodium hydroxide, not just hydroxide. So you have to put it as 2 sodium hydroxide like this. So your state symbols are equally as important. Let's put the gases here. It's a gas, and that one, let's put it in aqueous form. Okay, so that is how you form it right here. This will be your net, or rather your balanced overall reaction. It's balanced. If you check it, everything is there balanced. Oh, well, for your notes and for something that looks better than my handwriting, you may use this one over here, including the spectator ion. So you may look at this one instead. Okay, I hope you're noticing what's going on and how we got to this point right here. So it is now that I think you're ready to answer one examination type question, so you can just see how they ask you these things. Let's not delay that. So, you see, in the exam, these kind of things always happen. Really, they do. Because when we learned just now, let me go back and show you. Almost everywhere you look, notice our anode was on the left-hand side, right? And our cathode was on the right-hand side. Our power supply was up on top and everything. So, here now you go into your exam, and the first thing you notice is that your anode is at the right-hand side, your power supply is down here. It just, they know exactly how to just confuse you a bit, you know. So, but it's the same thing. Just think of it now as your anode is now this side. You can see that the positive terminal is here, the negative terminal is here. So this will be your inert electrode. As we have noticed, we can use those metals that we mentioned, such as titanium, even platinum, let's say graphite as well, as long as it is not going to react with our products. That's the main thing here. So what is supposed to get in from what we know? That's brine. And what was that brine? Please remember, it was your sodium chloride, and it has to be your concentrated sodium chloride here. Okay, it's concentrated that you pump into the anode. They used salt. It's still the used salt that you go. It's the dilute. We said it will be dilute here. Sodium chloride that is going to that side. This membrane, I said it was a selectively permeable membrane. Do you still remember which ions can go in? Well, I said only cations can pass. So anything that is negatively charged will not be able to pass. So you are seeing how things have changed here. Let's go and answer the questions. What is brine? Well, I think that one should not bother you. That's your sodium chloride. Okay? Identify the gas B produced by the positive terminal. So it means you're here at the anode. So what is this gas that's going out here? Which gas is this? You know? So how do you figure out which gas that is? Well, like I said, there is sodium here because it's being pumped in, right? So because of electrolysis, they will be existing like that, these things. And then we still have chlorine going on there. So what happens at the anode? Well, we know it's oxidation that takes place. And I believe at this point, you now know that it's chlorine that we get out from there. Just let me write that C properly for most of you to see. There. So which one is that gas? We know that it will be chlorine because this is what happens at the anode. Then we get 2 of those plus the 2 electrons. We talked about this. So which gas is this? It is chlorine gas. Very easy to answer. Is there any? So you know what we know is that sodium will come this side and then it will go for the electrons. But the problem is that we also have water coming in here, and even water is going for those electrons. And we said, let the beta oxidizing agent be reduced here. I think you still remember that we agreed that water was the beta oxidizing agent than sodium. So it's the one that will be reduced. So let's answer the questions rather. The questions say, consider the following standard reduction potentials, and here they are. We talked about those ones just a few minutes ago. Explain why water is reduced instead of sodium. Well, like I said, maybe we should just write it down this time. Water is a stronger oxidizing agent. Okay, that should happen a little bit faster than sodium plus sodium ion. So therefore, as you can see, it's a stronger oxidizing agent. You can see that it will be easier to have this reaction occur rather than that. Well, so it is what happens right there at the cathode. Okay, write down the formula of compound C. We just have to figure out where compound C is on the diagram, and we are not disappointed at all. It's this one. Well, it's at the cathode. So since it's at the cathode, is the product we form at the cathode. I think you remember the gas A, if you look at gas A, that certainly has got to be which gas? I think you can tell it's hydrogen, because chlorine should get out of here. Hydrogen there. So the only other product we have is sodium hydroxide. That one. So let's see what's what. Here we just write it as sodium hydroxide. Really, that's compound C. That's this one. And I just really like state symbols. What is the function of the membrane? Now, if you ask for that, so please just know that the membrane is there to prevent the solutions from mixing, but to allow only positive sodium ions to pass through. So that's the main thing. If the membrane was not there, our products were going to mix. No, rather not products this time, but our solutions were going to mix. So to prevent the solutions from mixing, and also to only selectively permeate these ions. So it's to let the positive sodium ions through. I think it's a very easy thing to see. Now, does the power supply provide AC or DC current? Well, we talked about this. We said it was direct current that we use in our electrolytic cells. The alternating current changes direction every half a cycle. And if it changes its direction, it means we will have, it will change our anode and our cathode and our anode and our cathode. So our oxidation, our reaction, instead of occurring, then there will be reduction taking place there. So we do not want that to happen. Oh, and the question just said, give a reason for your answer. Well, maybe now we have to write it down. So we are going to say the alternating current will cause the reaction to reverse. It will cause the reaction to reverse, so we are not going to do that. Cause the reaction to reverse. So that is what you have to keep in mind. So we have to all the time use our direct current in these electrolytic cells. So if you were listening and you understand this, I think it's a short lesson. The chloro-alkali industry, it's a very interesting thing. All right, so just know that it has lower environmental impact. It doesn't have those like greenhouse gases that it produces. So of course this one will be the better option to form your chloro-alkali industry. So thank you very much for watching this video.